finish. We started the day with Azadeh's talk, and we will finish with Azadeh's talk, and she will be answering some of the questions that she left open this morning, coarser equivalences for causal concurrency.
Okay, yes, me again. This is joint work with Umang, and probably after this he will have more energy to answer the questions than I do. But let me make sure that this is connected, because it's not reacting yet. Anyway, if not, I'll just use this. So this story starts with focus on the concept of equivalence relations on program runs. And you heard me talk about things, you heard other people talk about things. I wanted to kind of pay attention to this definition for a second, that because we are in a particular context of runtime monitoring, what we care about out of an equivalence relation is soundness, is that whenever we take a run, any other run that is equivalent to it is also a run of the same program, right? So it's basically, I've seen a run, all the other ones that I'm declaring to be equivalent to them, I can also infer them to be the runs of the program. So this is soundness. Then once I have a sound equivalence relation, I can define the core problem that we are studying in this paper, which is called the problem of causal concurrency, or the dual causal orderedness. So you have a set of equivalent runs. If two actions that appear in all these runs always appear in the same order, it means that their order matters according to that equivalence. So we call them causally ordered. But if it's okay that in an equivalent run the order of the two actions change, then we call them concurrent. So what we did in this problem is study the decision problem for causal concurrency or causal orderedness. So the decision problem basically picks two actions and asks, can we declare them ordered or concurrent? And this is very relevant to runtime monitoring. I give you just one example, but there are others in which if we pick two accesses to shared variables that at least one of them is a write, and we know that they're causally concurrent, we have found ourselves an actual data race in that program run. So it's kind of like the core decision problem that would let me check for data races. And then there are other examples. First thing that we did is we took one of the most famous kind of notions of equivalence from the literature, which is called the reads-from equivalence. And to define it, we have to focus on a particular alphabet of actions now. So imagine reads and writes to shared variables and thread IDs appearing in individual actions. And then the reads-from equivalence declares two runs equivalent if, first, the actions from the same thread that appear in two runs appear in the same order, so you cannot reorder within a thread. And then the second thing is every read has a most recent write, so it reads the value from that write, and that cannot change from one equivalent run to the other. So if you have satisfied these two things, if you think about it for a second, you will see that if one run is a run of a concurrent program, then any other equivalent run by this notion would be a run of an equivalent program. And this one happens to be sound, but also the coarsest equivalence relation that is sound. So beyond this, at least with this much information in the alphabet, we cannot have soundness, anything looser than this. So we studied the decision problem of causal concurrency and causal orderedness under this equivalence, and it turned out to be hard. The core hardness is that if you want to do a streaming algorithm, you cannot do it in constant space. You have to have at least a space proportional to the length of the execution. There are a bunch of other kind of hardness issues that are in the paper. I'm not going to go over them because I want to spend the rest of the talk talking about this particular one, which is the key one. So if you have this sort of hardness and you're dealing with really, really large logs of systems in which you're looking for violations, you're in trouble because your monitor has to basically have storage space proportional to lengths of the runs, which are millions and sometimes billions of events. So we don't want to do that. We want something better. And if you forget about reads from equivalence and ask yourself, okay, that coarse equivalence bad, what about other equivalences? Can this problem become simpler in those cases? Then there is a classic notion, which I talked about already today, that if you have a commutativity relation, it induces an equivalence relation automatically on program runs. And there is a commutativity relation on the same kind of alphabet of actions that then would be sound. So I would not let you reorder or swap things that belong to the same thread. So this way you will preserve the order of things in the same thread. And I will not let you reorder things that access the same shared variable and at least one of them is right. And this would preserve the most recent write before any read. So in some sense, I can defer to the soundness of reads from equivalence and say, anytime you make any of these swaps, you will remain sound. The runs will remain equivalent, and you can infer them to be the runs of the same program. Now, it's sort of a folklore knowledge, but we kind of give the description anyway in the paper because there is no precise citation for it, that under this equivalence, the causal orderedness or concurrency can actually be monitored using a constant space algorithm. So all of a sudden, things are much better. You don't have to have a space proportional to the length of the run. So then we found ourselves in this kind of in the middle of these two ends. A nice coarse relation, hard kind of complexity, much more tight relation, easy algorithmic result. And we asked ourselves, is there something in the middle? And just to tell you why we care about coarseness is the coarser you are, the more runs would be equivalent to a run, which means you're kind of doing your runtime monitoring or whatever over a much larger predictive set. So you want the more the merrier, basically, here. So, and the answer was yes, there is something in the middle of these two. And the solution came from taking the view that rather than focusing on commutativity of individual actions of your runs, you can actually look at blocks of these actions and talk about their commutativity as well, and arbitrary blocks for that. So for example, if I had marked those two tiny blocks for you, you would see that because that read and that write are non-swappable, under just commutativity of individual actions, you're sort of stuck with this arrangement. You cannot change it. Whereas if I take the blocks as they're marked, because each read is together with its corresponding write, they can kind of move together. And I haven't changed the read-write relationship that I told you I want to preserve. So these things we call grains, these blocks, and the grains don't have to even just belong to the same thread. So you can basically take any sequence of consecutive actions belonging to any number of threads and call it a grain. And then we kind of have a notion of equivalence based on such grains. So the moment we kind of do this view shift, things look easy enough. We say that, okay, up to a homomorphism, you can pretend your grains are your new letters, and then you can use non-determinism that everyone from automatic theory understands how it works to kind of guess all possible choice of grains. And then, as such, you will have basically, you're sort of defaulting yourself back to whatever method was working for individual actions under this sort of commutativity relation. And because you're guessing all choice of grains, you're guessing anyway individual actions as grains as well, you're just now adding more options to it. So you get something strictly better than the baseline. And this one can also be monitored, causal concurrency can be monitored for this in constant space. Except I deceived you a little bit. When I showed you this and I said, oh, those two, the reads are together with the writes, they can move. Yes, that part was correct. But it matters what comes after this. So if after this I have another read, that other read was originally connected to the write on the right. And if I swap the orders, it's going to kind of now match with the write on the left. And this is going to break things, right? So I weighed my hands. I didn't really tell you the whole story, but there's a difference between these two scenarios. But if the next action on variable x is a right, I'm good to go. I can swap those things because any other follow-up read is going to match to that right or something later. So this kind of gets us to the point that this sort of context after grains matter. They matter in whether I can soundly actually commute things. So the soundness of the commutativity relation now depends on this context, but it's really not a worry because we can always choose grains, and then based on the choice of grains and our choice of whether we decide to say that they commute or not, we can discharge this sort of conditions on the follow-up context and check that our choice in the future is unproblematic. So to kind of show you the big picture again, the same idea, we kind of have those ideas that I mentioned before, but now we can also add non-determinism one more layer to say that I will just guess my commutativity relation. And the moment I made a guess, now I'm committed to make sure that the future is okay with my guess, that context that appears afterwards. And if it's not, I will just abandon this kind of choice. If it is, I will kind of stick with it. And all kind of hand waving works fine, and I will have an actual sound now way of verifying these things. Of course, once this worked out, we got greedy. We said that, okay, here is kind of like a schematic thing in which I really badly want to be able to move those x operations against the other x operations, but this kind of one grain of salt or sand appears in the middle and is stopping me from reordering those two grains because they share a thread, and reordering them would be violating thread orders. So I want to actually be able to pick the grains you see on the right, but the grains on the right are not contiguous anymore. And this kind of got us to this concept of scattered grains. And with the scattered grains, I can kind of tell you the shorter story of, yes, we can handle scattered grains as well, but somehow, as a surprise to us as well, the notion stops to be a kind of purely commutativity-based notion. Because once you kind of have scattered grains like this picture, you can see that my grain G2 is sort of stuck inside my grain G3, right? And talking about these two grains that are sort of entangled to each other and talking about commuting them is a little bit of a nonsense, right? Exactly, this is one example, but exactly for cases like this, rather than make this a notion purely based on commutativity, we sort of build this graph that throws constraints between the grains and says, what grains should be ordered, what parts of what grains should be ordered before the other things, and then we can answer the question of causal orderedness or causal concurrency based on analyzing this graph, which we call a grain graph instead. But of course, I'm jumping over a lot of details which are in the paper. So we make this happen using all the trickeries that I mentioned to you before, with the choices of non-determinism, guessing grains, all of that. But I wanted to, I don't have time to give you the solution, but I wanted to mention the challenges that are there to actually have a constant space algorithm based on this grain graph. So the moment you have scattered grains, first of all, grains can kind of start and end arbitrary in the future. So there is this kind of contiguity is out the window. This doesn't immediately kind of sound bad. Then you kind of realize that when you have scattered grains, you can at any point in time have an unbounded number of grains that are open. That means you're in the middle of them. This means that that graph, if you're not careful, is going to have unboundedly many nodes, which is against a constant memory kind of algorithm. And finally, through other grains that come later, you can have these constraints form between grains that have already been in the past, started and finished, and you decide that there is no constraint between them, but some other things happen in the future that are going to indirectly connect them. So one has to be clever about this algorithm, but I'm kind of just giving you the good news that we have tricks that we can resolve all of these issues and have a constant time algorithm for this version as well. Now, I have 2 minutes. I'll finish on a future kind of looking view. you kind of saw me wave my hands and say, we use non-determinism for this, we use non-determinism for that. All of this is fine if you just want to give a theoretical result that this is doable in constant space. But of course, the moment you want to actually implement this, all this non-determinism on the parameter, on all the other parameters that are not the length of the run, for example, the number of shared variables, the number of threads, they become an issue. So if we wanted to really have a serious implementation for this, we really need a way of carefully, cleverly resolve this non-determinism so that the monitor on the constant side of things does not become too heavy. So that's part of the future work. I sort of already mentioned earlier today that this is just kind of one decision problem, causal concurrency for runtime monitoring. There are like tons of other decision problems that are related to testing or verification. It would be nice to see whether something like this or something similar to this would help us with those decision problems, making coarser commutativity applicable to those domains. And finally, it would be kind of nice to see that we have put one foot forward. We have now these grain-based notions. Is there still something further after this before reads from equivalence that can give us even more kind of relaxed equivalences over concurrent programs that we can exploit in all these domains?
Thank you. 5 minutes for questions. And again, a lot of contention.
No, I mean, I just have a stupid question, possibly. So when you say like constant space, do you assume something like the number of possible actions is bounded or something like that?
Because no. That is exactly constant space on the number of actions, so the length of the execution. The ones that I'm not constant on are the number of shared variables and the number of threads. So those are the parameters that I assume to be constant.
Hello, sorry, this can also be silly, and thanks for the talk. I was wondering, it was reminding me of some results, for example, on various equivalents, for example, on the runs of contextual Petri nets and so on. And I was wondering if you had to check if there is any connection with
contextual Petri nets?
Yep.
But in what sense contextual?
Meaning
I haven't heard of the term, that's why I'm asking.
Oh, well, simply meaning that basically you have some kind of asymmetry and then you have to decide causal dependencies, not just based on commutativity, but analyzing exactly the behavior.
Oh, I see what you mean. So you can really view this as that commutativity that is there. We are kind of trying to expand it from just commutativity of atomic actions to commutativity of groups in some sense, right? To expand this. So if we can figure this out, then maybe we can bring in symmetry and things like that and mix all of this together. But it's just kind of pushing the front on one dimension at the moment.
Thanks.
Other questions and comments? So I have got one in the meantime. You said that something that intrigued me. You said that it is possible to have grains that are closed, but something happens and they are unrelated so far. Something happens in the future, makes them related. So I found that very puzzling.
I might have something in this picture already that I can show you. So, in some sense of the word, if you look, there is a path that goes from G1 to G2. G1 top left to G2 the rightmost, okay? But that path was only closed. I had the G3, G2 connection. I had the G1, G4 connection, but the path was really closed down here. If you think that all these dots are like a million events later on this execution, I established something between G1 and G2 that were long gone, long over, down here like a million events later when the lowest kind of pink arrow that you see appeared. And this is exactly the problematic thing, right? They're gone. I want to really forget about them because if I don't have a strategy to forget, then my memory keeps growing. but I need to be able to then say, oh, you know, this arrow. So you need to remember, but you can't remember too much. This is really the balance.
Thank you. Other questions? Comments? Okay. I think we'll ask you afterwards if you have got still the capacity. Thank you very much.
Thank you.